What's going on, guys? Let's look at this problem right here. Here this question is asking, in the circuit of figure, determine the maximum value of R2 that guarantees operation of Q1 in the active mode. Assume beta is equal to 100, Is is equal to 10 to the power of minus 17 ampere, and Va is equal to infinity. Here the question is asking us to find out the maximum R2 value. Now let's see how we can do that. First of all, we have to know Vt value is a constant, that is 26 millivoltage, and IC can be calculated using this formula: IS times e power VBE divided by Vt. Therefore, VBE divided by Vt is equal to, if you take ln both sides, that's going to be ln of IC over IS. Okay, I just brought IS to this side and take ln, so E cancels and we get ln on the other side. Okay, now from this one we can derive the equation for VBE, that is equal to Vt times ln of IC over IS. Now if we apply Kirchhoff's voltage law for this circuit, we will get minus VCC plus ICRC plus VCE plus IERE is equal to 0. Here instead of IE we can do one thing. We can replace this IE with IC over beta. IC over beta, and we can keep this IC as it is, this VC as it is, and let's rewrite this one: VCC plus ICRC plus VCE. Instead of this IE, we are going to plug 1 plus 1 over beta times IC RE. Okay, instead of this IE we replace this one with beta, 1 plus 1 over beta IC, that is equal to 0. Now finally, from this equation finally we can derive an expression for VCE. VCE can be written as VCC minus IC times RC plus 1 plus 1 over beta times RE. Now in the active mode, let's continue here. In the active mode, VCE should be greater than or equal to VBE. Therefore, here VCE can be also equal to VBE. It's equal to or greater than to be in active mode. Active mode. So we can just equalize this whole thing to VBE. VCC minus IC RC plus 1 over beta times RE, that's equivalent to VBE. According to this whole thing is VCE. That's what we derived right here. Now for VBE we have this equation. That's what I'm going to plug right here. Vt ln of IC over IS. Okay, now we have this equation. Now let's go ahead and plug all the values we have. VCC we have 2.5. IC we don't have the value, so here we can solve for IC, because except IC we have all the values we have all the values, so we can solve for IC and RC is 2 kilo ohm. So let's put RC is equal to 2 kilo ohm plus 1 over beta is equal to 100, and RE is equal to 100 ohm times 100 ohm, that is equal to Vt is a constant value, that is 26 millivoltage. Ln of IC is what we are trying to find. Is is this one, 10 to the power of minus 7. And if you rearrange and solve for IC, you will get IC is equal to 0.793 milliampere. Okay. Now this is our IC value. Now we can go ahead and calculate VBE value. Since we have IC, we can calculate VBE because we have all that other values. VB is equal to VT ln of IC over IS, and VT is 26 millivoltage, ln of IC we just calculated 0.793 milliampere divided by IS, that is 10 to the power of minus 17, and that gives us 0.832 voltage. Now the next thing is we are going to calculate Vx. To calculate Vx, we are going to use the voltage division. Vx is the voltage across this R2. Okay, to calculate this one, we can use the voltage division. That is VCC times R2 divided by R1 plus R2, and that one, and Rx is equal to R1 R2. This is Thevenin equivalent voltage and Thevenin equivalent resistance, R1 plus R2. Now let's get rid of these initial parts. And let's continue here. Okay, KVL at input. KVL at input. If you apply KVL at input, this is going to become minus Vx plus Rx IE plus VCE plus RE IE is equal to 0. Now here we can take, instead of this Vx, we can replace it with in terms of VCC, and also instead of this Rx here, instead of Rx we can plug this one, and if we write everything in terms of R1, R2 and VCC, those kind of things, we will get the equation like this. VCC, instead of Vx I plug this one, VCC times R2 over R1 plus R2, plus instead of this Rx we are going to plug this one, that is R1 R2 over R1 plus R2 times times IC over beta, IC over beta plus VBE plus RE times 1 plus 1 over beta times IC is equal to 0. Okay, now let's go ahead and plug all the values. We have VCC, that is negative, VCC value is 2.5 voltage, times R2, we keep the R2 as it is, that's what we are trying to find, and R1 is 30 times 10 to the power of 3 plus R2 plus R1 is 30 times 10 to the power of 3 times R2 divided by 30 times 10 to the power of 3 plus R2 times 1 over 100 times 0.798179 times 10 to the power of minus 3 plus 0.832 plus 100 times 0.793 times 10 to the power of minus 3. Okay, the whole thing is equal to 0. And here if we solve for R2, we will end up with 20.239 kilo ohm. And that's our resistance R2. And that's the question is asking for determine the maximum value of R2 that guarantees operation Q1 in the active mode. We know that in the active mode VCE has to be equal to VBE. So we created the equation. First we created the equation for VCE. Then we know that the equation for VBE is VT ln IC over IS. So we equate both sides, and then we applied KCL at input, KVL at input, and we found out the Thevenin equivalent voltage and resistance, and wrote everything in terms of R1, R2 and VCC. Then we solved for R2 and found out the R2 value that will guarantee the active mode. And that's how we do this kind of problems. I hope you guys find this video helpful. Thanks for watching. And if you are trying to learn electronics too, there are a bunch of videos in my playlist. I hope you guys watch that too. Don't forget to subscribe. See you next time.